All right, let's talk about a problem that I'm pretty sure everyone in machine learning hits at some point. You know the one, where everything looks amazing in the lab, but then it just completely falls apart in the real world. It all starts with this one question, a question we've all asked ourselves.
I mean, you've been there, right? You build this model, you're feeding it data, and the numbers, they look incredible. Accuracy is through the roof, your loss is dropping like a stone. You're thinking, I've done it, this is the one. And then you show it some brand new data, stuff it's never seen before, and boom, performance just tanks. So what's going on here? So this is what that problem looks like in black and white. On one side, you've got the training data. This is the model's comfort zone, right? It's an A+ student here, 99% accuracy, no problem. But then, on the other side, you have the real world, new, unseen data. And it's like it has amnesia. That huge drop in performance, that gap is the classic sign that our model hasn't really learned the lesson. It hasn't learned to generalize.
And this villain, this problem, has a name: overfitting. What it really means is that your model didn't actually learn the patterns in the data. Nope, it just memorized the training set, including all the random noise and quirks. It's kind of like a student who crams for a test by just memorizing the answer key. The second you ask them a slightly different question, they're lost, because they never bothered to learn the actual concepts.
So how do you spot overfitting in the wild? Well, you look for this exact gap. The gap between your training error and what we call the validation error. That's the error on data it hasn't been trained on. When that training error is super low, but the validation error is way up here, that's your giant red flag. Your model just can't generalize.
Okay, so that brings us to the big question. Can we do something about this? Can we steer our model away from just memorizing and push it towards actually understanding? Can we get it to learn the general rules instead of just the specific examples? And the answer is absolutely yes.
And the hero of our story is regularization. Now, don't think of it as one single trick. It's more like a whole toolkit of different strategies. But the main idea behind all of them is to dial back the model's complexity. We're basically putting up guardrails to stop it from getting way too obsessed with the noise in the training data.
This is where things get really practical. If a model's complexity is the bad guy, how do we actively fight against it? How can we make it, cheaper for the model to find a simple solution instead of a complicated one?
The secret is to add a penalty term right into the model's cost function. You can think of it like a complexity tax. As the model trains, it's always trying to get its error as low as possible. By adding this tax, we're telling it, hey, go ahead, get more complex if you want, but it's going to cost you. This makes it find a sweet spot between fitting the data and staying simple. So tool number one is called L2 regularization, or sometimes you'll hear it called weight decay. With this one, the tax is based on the squared value of all the weights in the network. By penalizing big weights, we're basically encouraging the model to spread the learning out across a bunch of neurons instead of relying too heavily on just a few. The result? You get smaller, more distributed weights and a smoother, less complex model.
Now, there's a similar technique called L1 regularization. It's got one really important difference, though. The penalty here is based on the absolute value of the weights, not their squared value. Okay, I know, it sounds like a tiny change, but it has this really cool side effect. It can actually shrink some of the weights all the way down to exactly 0.
And that's the key difference right there. L2 is your go-to, your general-purpose complexity buster. It's a great default choice for just smoothing things out. L1, though, L1 is a specialist. By forcing the weights of unimportant features to 0, it's basically doing automatic feature selection for you. It creates what we call a sparse model that only cares about the most important inputs. Pretty neat, huh?
Okay, so penalizing weights is one way to go. But what if we could actually change the training process itself to build a tougher, more resilient network from the very beginning? What if we could force it to not depend on any one part of its brain?
And that leads us to this really clever technique called dropout. The name pretty much says it all. What we do is, during each step of training, we randomly drop out, or just temporarily ignore, a bunch of the neurons in our network.
Let's walk through it. So for one training step, we pick some neurons at random and just pretend they're not there. We do our forward pass, our backward pass, all with this slimmed down network, and we only update the weights of the neurons that are still active. Then, and this is the cool part, for the very next step, we bring everybody back and drop out a new random set. It's almost like the network is being trained with a different architecture at every single step.
So why on earth does this work? Well,
It's because no single neuron can get lazy and rely on its neighbors. Since any of its neighbors might disappear at any moment, each neuron has to learn to pull its own weight. This forces the whole network to learn multiple, independent ways of representing the data, which makes it way more robust and a lot less likely to overfit.
L1, L2, and dropout are super powerful, but, they do add a little bit of complexity to our setup. Is there a more straightforward, just common sense approach we could take?
You bet there is. It's called early stopping, and it is beautifully simple. All we do is watch our model as it trains, and we just hit the brakes at the perfect moment, right before it starts to overfit and its performance on new data starts to get worse. This little timeline shows exactly how it works. So, when you start training, both your training error and your validation error are going down. The model's learning, but eventually you'll hit this sweet spot where the validation error is as low as it's going to get. If you keep training past that point, your training error might keep getting smaller, but watch out, the validation error starts to creep back up. That's overfitting in action. The whole trick is to just stop right there at that sweet spot, and you'll have the best, most generalized version of your model.
Wow, okay, we have covered a lot. We've talked about 2 different ways to tax our weights, a way to randomly shut off neurons, and a way to just stop training at the perfect time. So the big question is, how do you know which tool to pull out of the regularization toolbox for your specific problem?
Think of this table as your little cheat sheet. L2 is a fantastic, super reliable place to start for just about any problem. If you think a lot of your inputs might be useless and you want a simpler model, try L1. If you're working with a huge, deep neural network, dropout is an absolute lifesaver for building robustness. And hey, for a simple, no-fuss method that just plain works, early stopping is your best friend. And you could even mix and match them. So, the next time your model is a total genius during training, but bombs in the real world, you'll know exactly what's happening. And more importantly, you'll have the tools to install the right guardrails. The only question left is, which one are you going to choose to build a model that doesn't just memorize, but actually learns? If this helped you get a better handle on regularization, do me a favor and hit that like button, share it with someone who might need it, and subscribe for more deep dives. Thanks so much for watching.